The story of Matt Armstrong working on a crashed Bugatti Chiron is not just about fixing a damaged car. It is about solving problems that most people would never even attempt to face. This was not a normal repair job where parts are ordered, delivered, and simply installed. From the very beginning, the project was filled with obstacles, and one of the biggest problems came from something many people might not even think about first: the cooling system. The Chiron is not like an ordinary car with one radiator. It has 10 separate radiators working together to manage the heat of a massive 1,500 horsepower engine. These radiators are responsible for cooling engine coolant, managing air temperatures from turbochargers, and handling other supporting systems that keep the car running safely under extreme conditions. When the car crashed, several of these radiators were damaged beyond repair. Normally, this would mean ordering replacements directly from the manufacturer, but that option was not available. Bugatti does not supply parts easily to independent builders, and in this case, there was no way to get replacements through official channels. That created a serious problem, because without functioning radiators, the engine could not run safely. Overheating would destroy the engine in minutes. This situation turned what might have been a straightforward rebuild into something much more complex and challenging. Instead of waiting months or even longer for official support that might never come, Matt and his team had to think differently. They needed a solution that did not depend on the manufacturer. That is where Bob came in, a skilled engineer with a deep understanding of how things work, not just how they are supposed to be repaired. The idea was simple but bold. If they could not buy the radiators, they would build them. This decision changed everything, turning the project into an example of creativity, determination, and independent engineering at its highest level. Understanding why building these radiators was such a difficult task requires a closer look at how they actually work. At first glance, a radiator may seem like a simple part made of metal tubes and thin fins, but in reality, it is a carefully designed component where every detail matters. The space in between tubes, known as tube pitch, controls how coolant flows through the system. If the spacing is too tight, the flow becomes restricted and the engine may not get enough cooling. If it is too wide, the surface area for heat transfer decreases, making the radiator less effective. Then there is fin density, which refers to how many cooling fins are packed into a given space. More fins can improve cooling, but only up to a point, because too many fins can block airflow, especially at lower speeds. On top of that, the size and shape of the tanks, the position of hose connections, and the placement of mounting brackets all need to match the exact design of the car. These are not random choices. They are part of a system that has been engineered specifically for the Chiron. Normally, manufacturers keep these specifications private, meaning independent builders do not have access to the exact measurements or design details. That is what made this challenge so interesting and so difficult at the same time. Bob did not have access to any official data, drawings, or instructions. All he had were the damaged radiators taken from a crashed car. To most people, these parts would look like useless scrap metal, but to someone with the right skills and experience, they were something much more valuable. They were a source of information. By carefully studying the damaged pieces, measuring what remained intact, and understanding how the parts were originally designed to function, Bob was able to begin the process of reverse engineering. This means working backward from the final product to figure out how it was made. It is not an easy task, especially when dealing with complex components, but it is a powerful way to solve problems when original data is not available. The first step in Bob's process was to carefully examine the damaged radiators and gather as much information as possible. Even though the parts were bent, broken, and partially destroyed, they still contained important clues. By measuring the remaining sections, Bob could determine the original tube spacing and fin density. By looking at the ends that were not damaged, he could estimate the size and shape of the tanks. The positions of hose connections and mounting points could also be identified from what was still intact. This process required patience, attention to detail, and a deep understanding of how radiators function. Once he had a clear idea of the specifications, the next step was to find suitable radiator cores. Instead of looking for parts specifically designed for a Bugatti, Bob searched for cores that matched the required dimensions and performance characteristics. This led him to an unexpected solution: radiator cores from a Honda Civic. At first, this might sound surprising, But when it comes to heat transfer, the principles are the same regardless of the brand of the car. What matters is not the name on the part, but whether it meets the necessary requirements. The Honda Civic cores had the right tube spacing, fin density, and size, making them suitable for the job. This decision shows an important aspect of engineering thinking, focusing on function rather than brand. With the cores elected, the next challenge was to turn them into complete radiators that would fit perfectly into the Chiron. This meant designing and manufacturing custom fittings, brackets, and connections. The cores themselves were only part of the solution. Everything else had to be built from scratch, and it had to be done with precision. There was no room for guesswork, because even a small mistake could lead to leaks or poor performance. The machining and fabrication process was where Bob's skills truly stood out. Using aluminum, he created hose connections that matched the exact diameter and angle needed for Chiron's cooling system. These connections had to be positioned perfectly so that the hoses would fit without stress or bending. At the same time, mounting brackets were designed and built to ensure that the radiators would sit correctly within the car's structure. This required careful measurement and planning, as the radiators needed to align with existing mounting points and avoid interference with other components. Fan mounting points also had to be included, allowing the original cooling fans to be reused. All of this work was done in a machine shop, using tools and techniques that require both technical knowledge and hands-on experience. Once all the individual parts were ready, the next step was assembly. The fittings were welded to the radiator cores, the brackets were attached, and the entire unit was checked for accuracy. This stage is critical because it is where any mistakes become visible. If a bracket is slightly out of position or a connection is at the wrong angle, it can cause problems during installation. In one case, a bracket was installed on the wrong side, which required correction. This mistake did not affect the overall quality of the radiator, but it highlights the challenges of working under time pressure. Despite this small issue, the radiators were completed and ready to be installed in the car. Considering the complexity of the task and the lack of official data, completing multiple radiators in just 3 days was an impressive achievement. The real test of the radiators came when they were installed in the Chiron and connected to the cooling system. This is the moment where all the work either proves successful or reveals hidden problems. The radiators were carefully positioned, bolted into place, and connected with hoses. Everything needed to line up perfectly, and according to Matt, it did. The next step was to test the system by introducing pressure. This process checks for leaks and ensures that all connections are properly sealed. As pressure builds, there are only 2 possible outcomes: silence or the sound of escaping air. Silence means success, while any sound indicates a problem. In this case, there was a small leak in one of the radiators. However, this was not due to a failure in the design or fabrication. Instead, it appeared to be caused by damage during transport. While this was disappointing, it was not a major setback. The solution was simple: repair the leak by welding the affected area. This quick response shows the advantage of having control over the manufacturing process. Instead of waiting for replacements or dealing with complicated procedures, the problem could be fixed immediately. This moment also highlights an important difference between independent builders and large manufacturers. While manufacturers rely on strict processes and supply chains, independent builders can adapt quickly and solve problems in real time. This flexibility is a powerful advantage, especially in situations where time and resources are limited. When compare what Bob achieved in 3 days to what might have happened through official channels, the difference is clear. Manufacturers like Bugatti operate within control systems where parts are supplied to authorized dealers, often with long wait times and high costs. In this case, there was no clear path to obtain the required radiators, and even if it had been possible, it could have taken months. Instead, Bob used his skills and experience to create a working solution in a fraction of time. This is not just about saving time or money. It is about demonstrating what is possible when people are willing to think differently. The radiators he built are not temporary fixes. They are fully functional components that perform the same job as the originals. This achievement challenges the idea that only manufacturers can provide reliable solutions for complex systems. It also raises questions about access to parts and the ability of independent builders to repair and maintain high-end vehicles. The story of this Chiron rebuild is not just about one car. It represents a larger shift in how people approach engineering problems. It shows that with the right knowledge, tools, and determination, it is possible to overcome even the most difficult challenges. In the end, what makes this story so powerful is not just the technical success, but the mindset behind it. Faced with a problem that seemed impossible, the team did not give up or wait for help. They found a way forward, proving that innovation often comes from those who are willing to take risks and think beyond traditional limits. As the project moved forward, the importance of what Bob had achieved started to become even clearer, not just to Matt Armstrong and his team, but to everyone following the rebuild of the Bugatti Chiron. This was no longer just about fixing a damaged cooling system. It had become a symbol of what independent builders are capable of when they are pushed into a corner. The Chiron is often seen as one of the most complex road cars ever built, designed with precision and controlled by a manufacturer that tightly manages access to its parts and repair processes. Because of this, many people assume that without factory support, a car like this cannot be properly repaired. However, Bob's work challenged that idea directly. By successfully building radiators that match the function of the originals, he showed that engineering is not limited to large companies with massive resources. It can also exist in smaller workshops where experience and creativity play a bigger role than official approval. This moment in the rebuild started to change how people viewed the entire project. What began as a risky attempt to rebuild a crashed hypercar was now becoming proof that knowledge and skill can compete with manufacturer control. It also added more pressure to the next stages of the build, because now there was something to prove. If the cooling system worked under real conditions, it would validate everything that had been done so far. If it failed, it would raise questions about whether independent solutions can truly replace factory parts. That is why the upcoming temperature test became so important. It was not just another step in a rebuild. It was a moment that would decide whether this bold approach had truly succeeded or not at the same time. The story also began to highlight a bigger issue within the automotive world, especially when it comes to companies like Bugatti. High-end manufacturers often control their parts and services very strictly, limiting access to approved dealers and certified technicians. This system is designed to maintain quality and protect the brand, but it can also create problems for owners and independent builders. In situations like this Chiron rebuild, where official support is not available, these restrictions can make repairs extremely difficult or even impossible. This is where the concept of independent engineering becomes important. People like Bob represent a different approach, one that focuses on understanding how systems work rather than simply following instructions. Instead of relying on manufacturer support, they rely on their own knowledge and ability to solve problems. This approach is not without risks, but it also allows for more flexibility and innovation. In this case, it led to a solution that would not have been possible through official channels. The use of radiator cores from a completely different car, for example, shows how thinking outside the usual boundaries can lead to effective results. It also raises questions about whether manufacturers should provide more support to independent repairers. While there are reasons for controlling parts and repairs, there is also value in allowing skilled individuals to work on these vehicles. The Chiron rebuild demonstrates that with the right expertise, independent builders can achieve results that are both reliable and impressive. This does not mean that manufacturer involvement is not important, but it does suggest that there should be a balance between control and accessibility. Without that balance, projects like this would never happen, and valuable innovation could be lost as the team prepared for final stages of testing. The focus shifted to making sure every part of the cooling system was ready for real-world conditions. Installing the radiators and passing a pressure test was a major step, but it was only the beginning. The true challenge was to see how the system would perform when the engine was running and generating heat. The Bugatti Chiron produces an enormous amount of heat, especially when operating at high power levels. Managing the heat requires all 10 radiators to work together efficiently. If even one part of the system fails, it can affect the entire setup. That is why careful preparation was necessary before adding coolant and starting the engine. Every connection had to be checked, every bracket secured, and every component inspected for potential issues. This level of attention to detail is essential when dealing with a car of this complexity. It is not just about making things work. It is about making sure they continue to work under pressure. For Matt and his team, this stage was both exciting and stressful. After all the effort that had gone into building and installing the radiators, everything now depended on whether they could handle the demands of the engine. This is where the difference between theory and reality becomes clear. A system might look perfect on paper, but real-world conditions can reveal unexpected problems. That is why testing is such a critical part of any engineering process. It provides a final proof that a solution is not only possible, but also practical. For Bob, this moment represented the result of his hard work and skill. For Matt, it was a next step in bringing the Chiron back to life. Looking at the bigger picture, the rebuild of this Bugatti Chiron is about more than just one car or one set of radiators. It represents a shift in how people think about repair, ownership, and engineering. In the past, working on a car like this without manufacturer support would have been almost unthinkable. Today, with access to tools, information, and skilled individuals, it is becoming more possible. The work done by Bob shows that even the most complex systems can be understood and recreated when approached with the right mindset. It also highlights the importance of practical knowledge, something that cannot always be learned from manuals or official training. Experience, problem-solving skills, and the ability to adapt are just as important as technical information. For viewers, this story is inspiring because it shows what can be achieved through determination and creativity. It challenges the idea that certain things are out of reach and encourages people to think differently about what is possible. At the same time, it does not ignore the challenges involved. This was not an easy process, and it required a high level of skill and effort. However, the success of the project proves that these challenges can be overcome. As the rebuild continues and the Chiron moves closer to being fully operational, the impact of this work will continue to grow. It will influence how people view independent repairs and may even encourage more builders to take on similar challenges. In the end, the story of these radiators is not just about cooling a powerful engine. It is about pushing the boundaries of what can be done outside of traditional systems and showing that innovation often comes from those who are willing to try something new. That as the moment of truth came closer, the focus returned once again to Matt Armstrong and the pressure he faced while preparing to run the Bugatti Chiron up to temperature for the first time since the rebuild began. This was not just another step. It was the point where everything would either come together or fall apart. The coolant was ready to be added, the system had been checked, and the repaired radiator leak had been welded and sealed. But even with all that preparation, there was still uncertainty. When dealing with a car this complex, especially one that has been rebuilt using custom-made components, there are always unknowns. As the coolant filled the system, it moved through every pipe, every connection, and every radiator that Bob had built. This was the first real chance of the system to show whether it could handle its job. Once the engine started, the temperature would begin to rise, and the radiators would have to do exactly what they were designed to do: remove heat efficiently and keep everything within safe limits. For Matt, this was a mix of excitement and tension. Months of work, countless hours in the workshop, and a huge amount of effort had all led to this moment. For Bob, it was a quiet test of his craftsmanship. He had done everything he could, measured carefully, built precisely, and corrected any issues along the way.